Okay, so for this one, we had to do some, uh, you know, in-class stuff that we weren't there for. So I just did my own little simulation that I knew would work. So this is what our dot plot is going to look like. So again, we're going to go 65 to 70 to 75 to 80, 85, 90, 95. Okay, now the premise is that again we are looking at test scores, except this time we have a sample of 4 people. No, I'm sorry, sample of 5 people. So our sample is now larger, and we do this 4 times. So you do 4 random samples, and then we compile our data. So our fake compiled data looks like this. We have a 64, a 69. Again, this is the mean. So these are means of several different samples of 71, 72, 73, and 75. We had 3 samples of 5 test scores that came out to have an average of 75. 2 76s, 3 77s, 1 78. Okay, that one got a little weird. Let's undo that. Oh no. Alright, I guess I have to use the eraser. Okay. I do not want to customize my pen. Okay. We had 5 79s. 1, 2, 3, 4, 5. Okay, we had 4 80s. 1, 2, 3, 4. We had 4 81s. 1, 2, 3, 4. 4 82s. 1, 2, 3, 4. 3 83s. 1, 2, 3, and 86. Okay. It's an 86. Just take my word for it. 2 88s. An 89. And a 90. Okay, so we are going to title this our sampling distribution. Of X with the line over the top. Okay, so this is the distribution of the sample mean. So these are all different sample means. Like we could, for instance, label this as 1 sample mean. This could be a second sample mean. Just like that. So our sampling distribution is made up of 40 different dots, so that's 40 times that I took a random sample of 5 test scores from my large, well, our class isn't large, but let's imagine that we had a large class size. So each dot represents 1 sample of 5 test scores, and we took the average, so we took the mean of those, and we took the sample mean. So each one of these dots is a different time that I picked 5 test scores and then found their average. So the true test average out of this random data bank that I used is actually 80. So our population mean was 80. And we're going to label this guy our population mean. Now we can see that about the middle of my sampling distribution, we see the population mean of 80. So if this is approximately normally distributed, then my population mean approximately falls right on my mean of the sample means. So a sampling distribution shows the means from all possible samples. Is the above dot plot a full sampling distribution? Well, this is only 40. If we had, I don't know, I put 100 random scores in my simulation. So there were 100 scores in the database, and there would be 100 choose 5, which let me go get a calculator and find out what that is. Okay, I went and got my calculator. So 100 choose 5 possibilities, that's 7, 5, 2, 8, 7, 5, 2, 0. Okay, I was looking at the calculator when I wrote that down. That doesn't look great, does it? Okay, I gotta stop doing that. Okay, let's try this. There would be 75 million plus possibilities. So that's how many total samples that I should have. I only have 40. So I only have 40 dots. So no, not a complete distribution. Okay. Number 5, we took a random sample of 5 scores at Rockford High. Okay, a random high school. Got a mean of 68. Is this convincing evidence that Rockford students did worse than the students at our school? Well, let's look at where a mean of 68 is on our thing up here. 68 would be right here. This is where they would fall. We only had one of our sample means out of 40 that was below a 68. So I would say yes, based on our distribution, the proportion of samples that had a mean lower than a 68, and that's going to be the P with the wiggly line over the top, is equal to 1 out of 40, which is equal to 2.5%. So 2.5% of samples were 68 or below. So that suggests that there is a 2.5% if Rockford had the same population mean. So there would be a 2.5% chance of choosing a sample with a mean less than 68, less than or equal to 68, if the population mean is the same. So that's pretty unlikely. So then I would say, yeah, our school probably did better. So we have some, oh, I don't want a pen anymore. We have some big ideas. So let's come on over here and let's write them down. Let's say are important. Why isn't it writing? Important ideas. Maybe that's a little better. I don't know. Okay, the first one is an unbiased estimator. So an unbiased as a statistic is unbiased if the mean of the sampling distribution is equal to the mean of the parameter. So a statistic is an unbiased estimator if the mean of the sampling distribution is equal to that of the true parameter. So what that would look like is, okay, here's our dot plot. And here's our population mean. I don't know why that pen looks, I picked the wrong pen. So this would be an unbiased estimator. Versus a biased estimator, which might look like this. And our true population mean is like over here. So our sampling mean like is here by this peak, but our true population mean is over here. So this would be considered biased. Okay, so our next important idea is the idea of variability. Let me try, what's this pen? I'm going to try this one. Oops. Got so excited I spelled variability wrong.